Right, so section 1.3 deals with matrices and matrix operations. So the matrix operations we are referring to here are basically adding matrices, subtracting matrices, and multiplying matrices. So multiplication and matrices, obviously that's going to work differently to the way we multiplied numbers. So we're going to define matrix multiplication in a very specific way. But before we do that, just recall that a matrix is a rectangular array of numbers. The numbers in the array are called the entries in the matrix. Okay, so that we'll refer to as entries as examples. The encircled numbers are the entries. The size of a matrix is simply defined as the following. We define a matrix size by the number of rows and columns. So we say a matrix, an m by n matrix, is a matrix that's got m rows. Those are the horizontal lines, and n columns, which are the vertical lines. So here in the first matrix, that will be my first row, my second row there. Okay, those are the horizontal lines I'm referring to, and then we have the vertical lines. So that will be the first column of the matrix, the second column of the matrix, the third column of the matrix, respectively. Okay, so those are the vertical lines we're referring to. So in a matrix, we always state the rows first and then the columns second. That's going to be standard procedure. Right, next up we have another point. One by n matrix is just called a row matrix or a row vector. So that would be a matrix where you've got one row and n columns. So this is an example here of a matrix that's got one row and it's got 3 columns. So it's a 1 by 3 row matrix. Okay, next up is a m by 1 matrix is called a column matrix or a column vector. Right, so in this case, this is a matrix with, it's got 3 rows and it's got 1 column. Okay, so that's a 3 by 1 column matrix. And just one other point is row or column vectors are normally denoted by a bar. Okay, and they can either be written horizontally or vertically. Okay, and now just a notational matter. The entry of a matrix A that occurs in the ith row and the jth column will be denoted by A with the subscripts ij. So I corresponds to the row and j corresponds to the column. Okay, so we also write a notation. We define the matrix A as it is illustrated in this case. This is a matrix A. It's got m rows and it's got n columns. Remember the rows. When you look at the indices, the rows always come first and the columns always come second. So just in a notational matter, this whole matrix can be written in a shorter form. It can just be written as A subscript ij, which indicates the entry in the ith row and the jth column, and the brackets on either side, and then you've just got this other index which indicates the size of the matrix A, which in this case is a matrix with m rows and n columns. Or you could just abbreviate that by writing it in that form there, which is just you have the 2 brackets on either side, and you've got the general form of the entries in the matrix A. Then another type of notation you can use is this notation here, which takes a matrix A and you're reading off the entry in the ith row and the jth column of the matrix A, and that is that entry there. Okay, so just as an example, in this case, the matrix A, the entry in the first row and the first column, that will be this entry here. Okay, so it will be the entry in the first row and the first column. Then just another point, a square matrix is a matrix where the number of rows and columns are exactly the same. So in that case, M will be equal to N, and that's an example here of a 3 by 3 square matrix. Then just the main diagonal of a matrix, that will refer to the entries where the indices are the same. So in other words, the row index is the same as the column index. Whenever the row and the column indices are the same of an entry, that is an entry that lies on the diagonal. So if we go back to this, if we go back to that sketch there, then you can clearly see that these will be the diagonal entries. Right, and in this case, we assume A to be a square matrix. In other words, we assume that the number of rows is the same as the number of columns. So they specifically require that a matrix be a square matrix there in that case. Then also the identity matrix, which we will talk about its definition a little bit later once we've defined multiplication. The identity matrix is the matrix that's got zeros everywhere except on the main diagonal. The main diagonal all have the same entries, and the entry is 1. Okay. Then let's look at operations on matrices. So for now, we say that two matrices are equal if they have the same size, so they have to be the same size for them to be comparable, and if their corresponding entries are all equal. Okay, and what that means, we say a matrix A is equal to a matrix B when both have the same size, right? So the matrices both have that their number of rows is the number of rows is the same, okay, and then they have the same number of columns. So N must be equal to S, and also what also needs to happen is the entry in the ith row and the jth column of A, which is that entry there, needs to be exactly the same as the entry in the ith row and the jth column of B, which is that entry there. And that has to be true for all indices I and J. Okay, putting that all in words, we need, as I said previously, the number of rows of A and B to be the same, and you need the number of columns to be the same, and also you need the corresponding entries to be the same as well. So the entry in the ith row and the jth column of A needs to be exactly the same as the entry in the ith row and the jth column of B, and that has to be true for all indices I and J. Right, so again, let's illustrate that just with an example. Right, so there we've got two matrices A and B. A is an n by n matrix, and B is an n by r matrix. So what do you want? When can we say that the matrix A is equal to B? When can we write equality sign there? Okay, you can write that B as being equal to A whenever you have the following. You have that the number of rows of A, which in this case is denoted by the index M, is the same as the number of rows of B, which is denoted by the index N. So M needs to be equal to N. Then you need the number of columns of A and B to be the same. So the number of columns of A is denoted by the index N, and that has to be the same as the number of columns of B, which is denoted by the index R. So N needs to be equal to R. So in addition to that, we also need the entry of A that lies in the ith row and the jth column, which is that entry there. That needs to be the same as the entry in B that lies also in the ith row and the jth column of B. Okay, and if we go and locate that entry, if we look down the rows and the columns, we go to the ith row and the jth column, that entry Bij there needs to be the same there. You need to be able to write an equality sign there. And you need to be able to do this for all the indices. No matter what you make the index I or j, we always need to have equality there. So that has to hold for all indices I and j. And when you have all those requirements met, then we can say that the matrix B is the same as A. Okay, next up we've got addition and subtraction. So the question is, how do we subtract matrices and how do we add matrices? So if A and B are matrices of the same size, so being of the same size is very important. You cannot add or subtract matrices of different sizes. So having the same size means they've got the same number of rows and the same number of columns. Then the sum of AB, denoted by A plus B, is the matrix obtained by adding the entries of B to the corresponding entries of A, and the difference, denoted by A minus B, is the matrix obtained by subtracting the entries of B from the corresponding entries of A. Okay, so notationally that means A plus B is the matrix obtained by taking the entry in the ith row in the jth column of A and adding that to the entry in the ith row and jth column of B, and you do that for all indices I and j. And then A minus B basically means the same, but you're just subtracting the entry in the ith row and the jth column. From that you're subtracting the entry in the ith row and the jth column of the matrix B. Okay, so there we've got an illustration. We have the matrices A and B. And before we can add them up, we need to make sure that they have the same number of rows, and they both have m rows, and the same number of columns, and they both have n columns. Right, so we can add them together. So the first thing we're going to do is let's calculate the entry in the first row in the first column of A plus B. So you're going to take the entry in the first row in the first column of A, and you're going to add it to the entry in the first row and the first column of B. Right? So we take that entry, and then we take the entry from the corresponding entry from the matrix B, and we add the two together, and that's my first entry. Okay, then next entry we're going to do, we're going to stay in the first column. We're going to look at the entry in the second row in the first column. So you're going to go to the second row of A and the first column. So you're going to take that first entry, and to that you're going to add the corresponding entry in the matrix B, which is the entry in the second row in the first column of the matrix B. So you're going to take that entry there and add it. Okay. And then what we're going to do is we're just going to complete the first column by taking the remaining entries of A in the first column and adding them to their corresponding entries in the first column of the matrix B. Okay, so there we take the remaining entries in the first column, and we take the corresponding entries in the matrix B. We add them all together there separately, and that forms my first column of the sum between the matrix A and B. So we can now move on to the second column, and we can do the same procedure for the second column. You can take the whole second column, each entry running from the first row right up until the mth row, and you're going to add their corresponding entries in the matrix B. And those will be the entries in the second column of the matrix B running from the first row to the mth row. So adding those entries separately together, we get the second column of my of the sum between A and B. Okay, then moving onwards further down the columns of A, we go to the jth column of A, and we work through from the first row right through to the mth row. So taking the entries of the jth column of A, and then taking their corresponding partners in B, and then adding them together separately. Right, so we take again the jth column of B, and we run through all the rows from row 1 to the mth row, and we add all those terms together separately. Okay, so we construct the whole jth column of A plus B. Okay, and we do it one entry per time. Okay, then we carry the process through until we get to the last column, which is the nth column, and there we're going to take the nth column of A, and we're going to take the nth column of B, and then we're going to run right through all the rows from row 1 to row M, and we're going to add those entries separately to form the last column of the sum between the matrix A and the matrix B. All right, so that is that's how the sum between A and B works, and in general, that's what the sum will look like. Just to make a note. So the entry in the ith row in the jth column of A plus B is the entry in the ith row in the jth column of A plus the entry in the ith row in the jth column of B. Okay, so that is a notation written down below, and that's the underlined term. So next up we look at the subtraction. Again, subtracting from AB, we need to make sure the number of columns and the number of rows are the same of the matrix A and B. So again, we perform the same procedure, but we just replace, in each instance, we replace the plus sign with a minus sign. So again, we get the entry of A minus B in the ith row in the jth column, and that is the underlined entry. Right, next up we have just a quick example. We've given the matrices A and B. We're asked to add A and B and subtract from A, B. So how do we do this? We make sure A and B have the same number of rows and columns. Both A and B have 3 rows, both A and B have 4 columns. So it is valid to add them. So we add them entry-wise. First row, entry in the first row in the first column, plus the entry in the first row in the first column. That is 2 minus 4, which is minus 2. Entry in the first row in the second column of A, plus the entry in the first row and the second column of B is 4. Okay, so then you add 0 to 5, which is 5, and 3 to 1, which is 4. Again, moving on to the second row, you add minus 1 to 2, which is 1, 0 to 2, which is 2, 2 to 0, which is 2, and 4 to minus 1, which is 3, and the last row, 4 to 3 is 7, minus 2 to 2 is 0, 7 to minus 4 is 3, and 0 to 5 is 5. Okay, and the same thing for the subtraction. The first entry in the first row in the first column of A, and from that you subtract the entry in the first row and first column of B. So that is 2 so that is going to be 2 minus 4, which is 6. 1 minus 3, which is minus 2, and then you carry the process through right up until the end. Okay, so that is how addition and subtraction, how it works. And then if C is a 2 by 2 matrix, can we add C to A? We most certainly cannot, because C has got 2 rows, whereas A has got 3 rows. And we know addition and subtraction only works with matrices of the same size. Okay, next up we've got scalar multiplication and matrices. So if you have a matrix A and C is a scalar, then a scalar multiple denoted by CA of a matrix is simply obtained by multiplying each entry of the matrix A with a scalar C. And notational wise, CA will be the matrix obtained by taking the ith row in the jth column entry of A and multiplying it with C and doing it for all indices I and J. So if we take the matrix A and the matrix B, then twice the matrix A, you're going to multiply the scalar 2 with every entry of A, so that 2 times 2 gives you 4, 2 times 3 gives you 6, 2 times 4 gives you 8, and the second column is the second row is the same, so that's going to be 2, 6, and 2. Then if we look at B and we take the scalar multiple of B, where the scalar is -1, you multiply each entry of B with -1. So you get the matrix 0, -2, -7, and 1, -3, 5. Now just one note, it is common practice to denote minus B by negative B. So -1 scalar multiple of B is just simply seen as the negative of the matrix B. The negative of the matrix B. Alright, next up we have an example that illustrates everything we've done up until now: addition, subtraction, and scalar multiplication. So it works very similar. The same algebraic principles that we use to solve normal linear equations apply to matrix equations. So there we are asked to solve for A in that given matrix equation. So B and C are both given as 2 by 2 matrices, and for addition and subtraction to work, we need the matrices to have the same number of rows and the same number of columns. So B and C do have the same number of rows and columns, and I is the identity matrix. So for this to work, I must be a 2 by 2 identity matrix. So basically, we can add the negative of the matrix B on both sides of the equation without changing the equality sign. So we add minus B on both sides. So on the left-hand side, the B matrix will cancel with its negative to become the 0 matrix. And on the right-hand side, we've got a sum of 3 2 by 2 matrices. Okay, so that's easy to simplify the left-hand side. That becomes 2A, and that is equal to the 2 by 2 identity matrix, which is 1 0 0 1, plus C, which is given. C is 2 0 3 1, 2 0 3 1, and then negative B, we know what that looks like. Before we multiply through the scalar, let's just write down B first, and that's 1 minus 1 minus 2 0. And then again, simplifying further, we first add the two matrices, the identity matrix with C, and we apply the same principles. So it's 1 plus 2, which is 3. Then it is 0 plus 0, which is 0, and 0 plus 3, which is 3, and then 1 plus 1, which is 2. And that we're going to add to the negative of B. The negative of B, negative 1 is the scalar, so we multiply each entry with negative 1. It becomes minus 1, 1, 2, and 0. And then we add those two matrices. 3 minus 1, which is 2, 0 plus 1, which is 1, 3 plus 2, which is 5, and 2 plus 0, which is 2. Okay. So now to finalize the problem, we solve for A by multiplying with a scalar on both sides, and this scalar is going to be 1 over 2. So we multiply the left-hand side with 1 over 2. Right, so we get 1 over 2 times 2A, and then on what we do on the left we need to do on the right. So we multiply the right hand side with a half, and therefore the matrix A becomes, on the left hand side we've got A, and on the right hand side we've got, we multiply that scalar, the half, we multiply it with each entry in the matrix. That's how scalar multiplication works with matrices. So that becomes a 1, a half, 5 over 2, and 1. Okay, now next we move on. We've covered scalar multiplication, subtraction, and addition. So now we move on to multiplication. So how do we multiply matrices? So if A is a matrix that's given to be an M by R matrix and B is given to be an R by N matrix, then the product between A and B is going to be an M by N matrix, and it will be constructed as follows. So if we want to know what the matrix A and B, A times B, what it looks like, we need to find a general expression for the entry in the ith row in the jth column of A times B. So the entry in the ith row in the jth column of A times B is defined as follows. The entry in the ith row and the jth column of a product is just the ith row of A multiplied with the corresponding entries in the jth column of B. And this can be written mathematically. So you take the entries in the ith row. There's my first entry in the ith row, second entry in the ith row, and my rth entry in the ith row. And remember, the matrix A is an M by R matrix, so there's going to be R columns. So here each row has R components. Okay, so you're going to take that row and you're going to go to the jth column of B. You're going to go to the jth column of B, and the jth column of B is going to have these entries. It's going to have these entries. The entry in the first row in the jth column, the entry in the second row in the jth column, and the entry in the rth row in the jth column. And remember, B has got R rows, and it's got N columns. Okay, so there we've got the two matrices, right? So what do? What does the entry in the ith row in the jth column of this matrix looks like? So that's just a generalized expression of what the entries in A times B look like. So the entry in the ith row in the jth column looks as follows. So what you do is you take the ith row, which is this expression here, okay, that row there. You take the first entry in the ith row, and you basically, that is going to be your first term. You multiply that with the first entry in the jth column of the matrix B, and the jth column is that column there. Okay, so you're going to take the first entry there, which is that entry there, and you're going to take it and multiply it with that entry there. Okay, that you're going to then add to the next entry in your ith row of A is that entry there. Okay, write that down, and then you're going to match it with the second entry in the column of in the jth column of B. Okay, and you're going to write that. Okay, and then you're going to continue onwards, and you're going to match those row entries with the column entries until you get to the last entry, which is that entry in there, and you're going to match it to that entry there. Okay. Okay, now please note that one important thing is that if you count the number of entries in the jth column of B, okay, the number of entries there, you count them as there are n entries. That index indicates the number of entries there. So there are n B's, and here in the ith row of A, if you were to count the entries there, there are also n entries. So you're always going to match the number of entries in the ith row of A with the number of entries in the jth column of B. Okay, and that is the necessity that needs to hold for a product between two matrices to be valid. Okay, so what needs to happen for a product between two matrices to exist? So we talked about A being a M by N matrix and B being a N by R matrix. Okay, so if you multiply the ith row of A with the jth column of B, then you need those number of entries in the rows and the columns to be exactly the same. So the number of entries in the rows of A is denoted by the column, is denoted by the number of columns. So there are n columns, and then the number of entries in the column vectors of B, that the index that counts that is the number of rows, which is n rows. So those two entries need to be exactly the same for a product between two matrices to exist. So the number of columns of the matrix that occurs first in the product, which is A, needs to be the same as the number of rows of the matrix that occurs second in the product. Okay, so how do we determine the size of the product between two matrices? So we look at these two indices, I and j. The I index in this case corresponds to a row of A, and j corresponds to a column of B. Okay, so to determine the size, we need to look at the range in the index I and the range of the index j there. So how many possibilities can this index I take on? Well, as I said, it corresponds to the rows of A. So let's count the number of rows of A. How many are there? There are m rows. Okay, so there are m possibilities that I'm going to have to consider for I. Right, so there are m possibilities there. And if we look at j, how many possibilities are there? I'm going to have to run through how many options? I'm going to have to run through all the columns of B. And let's go and count the number of columns of B. So I'm going to have to run through from the first column to the second column, right through to the jth column, right through to the very last column, which is the rth column. Okay, so there are going to be R columns of the product between A and B. Okay, and as I said previously, you always have to make sure that firstly, before you start anything, the number of columns in the matrix that occurs first in the product needs to be the same as the number of rows of the matrix that occurs second in the product, and that ensures that I can match the entries in the row vectors of A with the entries in the column vectors of B. So we need those quantities to be the same. So how do you determine the size then? You basically delete that, and that will then be your size. It will be an M by R matrix. The number of columns of the matrix A must equal the number of rows of B to be able to calculate A times B. Right. Okay, so let's just look at what the product in total looks like. So there's the matrix A times B with all its entries, and we're looking at the entry in the ith row and the jth column. And what does that look like? Well, go back to our expression. Entry in the ith row and jth column, we calculated it as that expression there. So you take that expression that you calculated. Okay, you have your expression there. You calculate it as a number, and what you do is you take that number and you plug that number into that position there, which is the ijth position, the ith row in the jth column. And then what you do is you do that for all your indices I and j. So the indices I run in this case from they basically run from 1 to m, okay? So it runs from 1 to m, and the indices j run from 1 to r. So they run from 1 to r. So you're running from 1 to m there, and you're running from 1 to r there, okay? So you've got r columns and you've got m rows. So it's quite a bit of calculation to do. Okay, so I just want to make one last notational point. Is this expression that we used, or the way that we calculated the entry in the ith row in the jth column of A times B, you can see that as what is known as a dot product between two vectors, right? So you take the remember we said we take the ith row of A, which is that expression there, okay, and that you can view as a row vector, okay. And then we said we take the jth column vector of the matrix B, okay, which is that matrix, which is that column there, okay, and that is a column vector. Okay, so that is a column vector. Okay, so there, those entries there. And now the dot product is simply the following. Okay, the dot product is simply the following. It's basically what we calculated previously. So I just want you to know the difference in notation, and that we will refer to the dot product sometimes, and it will normally be denoted by that dot there. So all you do is, when you calculate that, is again you match up the entries there. So you take that entry there, you multiply it with that entry there, okay, and then you add that to the next one, which is this entry here, okay, and you multiply it with the second one there, okay, and then again you carry this process through until you get to the last entry. Okay, so there you go, you're going to carry that through, match them all together until you get to your last entry there, and that you're going to multiply with that last entry there, the matching one. Okay. Like that. Okay, and that product, that defined product, is what's known as a dot product. It's a dot product between the ith row vector of A with the jth column vector of B. Okay, so here we've got an example. Let's see if we can calculate those products. Firstly, they ask us compute A times B. Right, so basically A is a 3 by 2 matrix and B is a 2 by 2 matrix. So we need to check that the number of columns of A is exactly the same as the number of rows of B. Okay, so clearly those two numbers are the same, so we can find a valid product between these two matrices. Okay, so A times B is, firstly, let's determine the size of A times B. So A times B, remember we said A is a 3 by 2 and B is a 2 by 2. Okay, so what is the size? The size of A times B is going to be a 3 by 2 matrix. Okay, so that's what the size of A times B is going to be equal to. So you do that by pretty much cancelling that number of the number of columns there, and then you cancel the number of rows there, and the two indices that remain, that will form your size. So this will correspond to your number of rows, and that will correspond to your number of columns. Right, so having established the size of the matrix A times B, we can now go and calculate it. So it's a 3 by 2 matrix. Right, so you take the entry in the first row, and the first column is going to be the dot product of that vector with that vector there. So that's going to be 3 times 4, which is 12, plus 0 times 0, which is 12. Then we're going to look at the entry in the second row and the first column. So you're going to take the second row of A, dot product that with the first column of B. So that's minus 1 times 4, which is minus 4, plus 2 times 0, which is minus 4. Then we're going to look at the next entry. It's going to be the third row of A multiplied by the first column of B, and that is going to be 1 times 4 plus 0 times 1, which is 4. Okay, so this is a 3 by 2 matrix. It's got 3 rows and it's got 2 columns. So moving on to the second column. So the second column is going to be determined by taking the first row of A and finding the dot product with the second column of B. So it's 3 times minus 1, which is minus 3, times 0 times 2, which is 0. So that's minus 3. Then we're going to take the next entry, which is going to be the second row of A, dot product with the second column of B. So that's going to be minus 1 times minus 1, which is plus 1, plus 2 times 2, which is 4. So that is going to be 5. Then the last entry, you're going to take the third row of A and multiply and dot product that with the second column of B. So that's 1 times minus 1, which is minus 1, plus 1 times 2, which is 2. So it's 2 minus 1, which is 1. Okay, so that is my matrix A times B, and it's a 3 by 2 matrix. All right, so let's look at the matrix B times A. Okay, so B times A is what we want to look at. So B, we said, is a 2 by 2 matrix, and A is a 3 by 2. Okay, so looking at the product now, for the product to hold, we need the number of columns of B and the number of rows of B to be the same. And 2 is clearly not equal to 3. So B times A cannot be determined. It cannot be determined. All right, so B times A is certainly not possible. Okay, so let's quickly look at this example. I'm not going to spend too much time on this. We know what how the product works now. What I'll do is let's look at number 2. Now, number 2 is we are asked to calculate the product between the matrix 5, 0, minus 7, 1, 5, 9, and we're going to take the that and we're going to multiply it with the column vector 3, 1, minus 1. Okay, so let's just quickly check this. This is a 2 by 3 matrix, and you're going to multiply it with a 3 by 1 matrix. So clearly this is a valid multiplication because the number of columns of the matrix that's first in the product is the same as the number of rows of the matrix that's second in the product. So basically this means that we will have a 2 by 1 matrix in this case. So that is what this matrix is going to look like. Okay, so the product then becomes, right, so we need to look at the first entry. So the first entry is going to be the first row. We're going to take the dot product with the first column of the second matrix in the product. So that's going to be 5 times 3 plus 0 times 1 plus minus 7 times minus 1. Okay, so again, that is going to be 5 times 3 plus 0 times 1 plus minus 7 times minus 1. Okay, and if you go and work that out, that is going to be, 22. Okay, that's going to be 22. So your first entry is going to be 22. Okay. Okay, then the second entry we're going to look at, we are going to take the second row and we're going to multiply it with the first column. I'm going to dot product it. Okay, so that again is going to be 1 times 3 plus 5 times 1 plus 9 times minus 1. Okay, and if you go and work that out, you get minus 1. Okay, so this again, this is a 2 by 3 matrix times a 3 by 1, which is a 2 by 1 matrix. Okay, so that is my product. Okay, looking at number 4, there you've got the column vector, and you are multiplying that with a row vector. Okay, so let's just look at the scenario here. So you're taking a 3 by 1 matrix and you're multiplying it by a 1 by 3 matrix. Check that it's valid. The product, the number of columns in the matrix that occurs first in the product is the same as the number of rows of the matrix that occurs second in the product. So essentially that is going to mean that we are dealing with a 3 by 3 matrix here. Okay, so we're dealing with a 3 by 3 matrix. So immediately you know what the size of this matrix is. It is going to be a 3 by 3 matrix. So let's work that out. So the entry in the first row and the first column is going to be the first row of the first matrix, dot product with the first column of that matrix. So that is going to be 1 times 4, which is 4. Okay. Then the entry in the second row in the first column is going to be, you're going to move on to the second row of my matrix, and you're going to dot that with the first column of the second matrix. So that's 1 times 4, which is going to be 4. Okay. Then we look at the entry in the first column and the third row. So that's going to be the third row of this matrix, dot with the first column of this matrix, which is minus 3 times 4, which is minus 12. Okay, so that's going to be minus 12. Then we move on to the entry in the first row in the second column. Okay, so we take the first row of the first matrix and we dot that with the second column. The second matrix, and that's 1 times 0, which is 0. Okay, then we look at the entry in the second row in the second column, which is going to be the second row of the first matrix dotted with the second column of the second matrix, which is 0. Looking at the third row and the second column, we take the third row of the first matrix and dot that with the second column of the second matrix to get minus 3 times 0, which is 0. And then moving on to the last column, the first row and the third column, we're going to take the first row of the first matrix and dot that with the third column of the second matrix and get 1 times 1, which is 1. Then we move on to the next entry, which is the second row of the first matrix dotted with the third column of the second matrix, which is 1 times 1, which is 1. And then the entry in the last row and the last column is the third row of the first matrix dotted with the third column of the second matrix. So it's minus 3 times 1, which is in this case minus 3. Okay, so there's our 3 by 3 matrix, and I'm going to leave question 1 and question 3 as an exercise for you guys to do separately. Okay, partition matrices. A matrix can be subdivided or partitioned into smaller matrices. These are called submatrices, by inserting horizontal and vertical lines between selected rows and columns. So as an example, we can partition A into basically 3 parts. A is a 3 by 4 matrix. We can take the first 2 rows and the first 3 columns and group them all together as one unit. Then we can take the last column and the first 2 rows and partition that into another segment. Then we can take the last row and the first 3 columns and group that together. And then lastly, we can group the remaining entry as another matrix, which is a 1 by 1 matrix. So you basically get a 2 by 2 matrix. Second example there is you can partition the matrix A into 3 row vectors, and you denote each row vector by R, or you can partition A as 4 column vectors. That is something you can also do. Now we can actually partition matrices and row and column vectors and then express the product of 2 matrices where you use this particular row